we now arrive at the core of this course, of this class, which is the synthesis of control laws. So basically this is the goal for which we have been preparing and for which we have been doing all we've done so far. All the things we've done so far are just preparation and preliminary knowledge that you need in order to be doing this, which is the important thing, the goal, the practical goal of this class, in the sense that this is the thing that you should be able to do as a result of this teaching, because this is the useful thing. What is the useful thing we're talking about? Is the design of a controller. So what we have seen so far, we have seen controllers in this scheme, in this form, so with the feedback structure, where H is the plant, so-called plant, means the system is given to us, so the system needs to be controller, the plane, a car, any device you might think of, which has inputs U and output Y. So we have some specifications for what Y has to do, probably in a reference to a given set point, this YRF. And the goal here is to design, to find the law, basically, if you want, the transfer function, which correspond, as you know, to linear ordinary differential equation, the transfer function which does the job. And H instead is given. It is one of the given data of the problem. So we have seen it already many times, but I will insist on it again. So the goal on a control engineer, of a control problem in general, is given a certain plant, a certain system, certain transfer function, in this case linear, given a certain specification, set of specification. We have seen what kind of specification we can have. We can have specification on the static value of Y with respect to reference. We can have a specification on the dynamic value of Y with respect to a dynamic reference, response to a ramp, for example. And we can have a specification in terms of robustness, in terms of speed, etc. And of course, the necessary condition for all of this is that the closed loop is stable, right? So how do we do this? So the question we need to answer in order to answer this question is how we should choose this controller C. This is the main goal, to satisfy the specification. How should C be parameterized so that we can make the choice simpler? Should we choose C among the infinite set, the densely infinite set of all the possible transfer functions of order 0 to infinity? Or maybe should we try and limit ourselves to some specific kind of transfer function which do the job better than others? And then again, how to guarantee stability and robustness of the closed loop. So this is the classical scheme we have seen, the simple feedback loop. H is given, C is to be designed with typically a negative feedback, which is conventional, but it helps. You might find in the literature, in the problem, some other schemes, for example, the feed-forward scheme, which yields this reference to output function. Notice that the numerator is a bit weird, but at the denominator we always have the same guy, 1 plus CH, 1 plus L, the loop transfer function. And then you might even have multiple loops, like look at this one. You have a first closed loop between H1 and C1, where L is H1, C1, and then you have a second closed loop over here, still with negative feedback, with C2, H2, and the resulting transfer function between this and this value, which is, as you know, H1 divided by 1 plus C1, H1. So the loop transfer function of the first loop is H1, C1. The loop transfer function of the second loop is C2, H1, H2 divided by 1 plus H1, C1. And then you can also compute which is the value of Y ref to Y2 Okay, you can see in one of the tutorials we have this kind of structure, and you will see how it works out. And the idea is of this scheme and also the previous scheme is to introduce more degrees of freedom, but not all in one shot, but just one at a time, because in this case you can solve first this loop over here, and then you can solve the second loop. You might have specification on y1, for example, and then specification on y2. So how do we find, for this scheme, the classical simple feedback loop scheme, how do we find the C? How do we find the controller, the control law? Well, you might just write down y over yref, the output over the reference, and you see that this is what we get. And typically the specifications will steer you towards a certain given dynamics, a certain given behavior for this function. For example, you want to have a certain pass band for this function. You want it to be stable, of course, and you want to have it a certain static precision, etc. So what you might be tempted to do is just take a model closed loop function, so a model for this y over yref, we call it f, and then you just set this function equal to f, and then you can compute C just by solving the equation. This looks like a good idea, but it is not, because first of all you have no idea what CS will be. It could be stable, unstable, causal, non-causal. Non-causal means that cannot be realized in practice. And there might also be some hidden dynamics that get into the picture. For example, if you have a non-stable pole in F and in H, this pole will be simplified and will also be simplified in the loop transfer function. And then you might notice that this thing you will not see it. Let's imagine, for example, that you have an unstable pole in C, and you just put the corresponding unstable 0 in H, or vice versa. Then it will mean that in L you will not see this unstable pole, but there will be an unstable dynamics between epsilon and u, or between u and y. So basically, in general, it is very dangerous to have a zero pole cancellation if these poles are unstable. So this, just to make a long story short, is not a good idea for one of these reasons. And again, you don't know if the system will be robust or not. By robustness, I remind you that we mean how much C can change in terms of, for example, phase or gain or modulus before you become unstable. Here you just solve for one value of C, but you don't know if it changes a little bit what's going to happen. So this approach looks good, but it is not a good idea. So in general, we use another approach. The good approach is to basically rely on the property of the closed loop as a function of the loop transfer function. And this basically is relying on the Bode criterion, on the Bode diagram of the loop transfer function. I repeat, of the loop transfer function, C times H, not of y over yref. The loop transfer function from C times H is what we use to determine whether the system is stable in closed loop, whether the system is robust, what are the robustness margins, and also it can be used, as we've seen, to determine a lot of the properties of performance of the closed loop. The only negative point of this approach is that we really need to have no poles with strictly positive real part in H, and then we will take care that we do not put additional poles of this kind in C, because this is the necessary condition in order to apply the Bode criterion, the critère du revers. So what means that instead of targeting a desired f for y over yref, we rather target a given L, a given loop transfer function, which is the product of C times H. And this L will be the thing that will guarantee stability and performance and margins. Okay, so considering H is given, we work on C, and of course we work on the Bode diagram of C times H. So we will need to start from the Bode diagram of H, assuming C is 1, and then little by little extend C in order to obtain the L, the C times H we desire. And there are two possible ways to do it. Either we choose a standard form for C, should be rich enough degrees of freedom in order to achieve what we want, and this basically means choosing standard controller forms. We will see these controller forms shortly. They have some strange names, which we will learn in a second. And then if you already choose this form of a controller, then the only thing you need to do is to tune the parameters, because the structure, the formula, the equation is already given. The transfer function is already given. Otherwise, the second possible way is to just tune the control parameter and the structure at the same time. This is what we call the loop shaping approach, loop shaping, which will not be detailed in the course of this class, unfortunately. So we will focus mainly on this predefined control structure. And then in order to tune the control, you need to have the specification translated into frequency domain. So for example, we have passband specifications for the closed loop, for the F. These passband specifications are equivalent to crossover angular frequency specifications. If you remember the passband, what it is the limit of the plateau of the transfer function. The transfer function from yref to y starts usually flat and then it declines at a certain point and goes sloping down. And this frequency, this angular frequency at which we start sloping down, is the passband, the limit of the passband. And we have seen the limit of the passband is roughly equal to the crossover angular frequency for L. What is the crossover angular frequency of L? It is the value of angular frequency for which L hits 0 dB. Then you might have robustness specification, and then they just translate directly into phase or gain margin, and you can just set them directly on the picture, on the diagram of L. You might also have specification on the damping of the poles of F, or the closed loop function, and these are basically related to the phase margin, as we will see in the next slide. And also, last but not least, you might have a specification on the steady state error with respect to a step, a ramp, etc. And as we've seen in the previous class, this will basically require the addition of integrators in the loop. So basically, you will have the controller being composed by a term 1 over s or 1 over s squared, etc., etc. Concerning the damping, in general, we can see that the damping factor and the overshoot as well, and the overshoot, you remember, is how tall is the peak when you have a second order pole, for the closed loop function, are related to the phase margin. These are just an example of what you might have. So they are specific for a given transfer function, but it is general for what concerns the trends. In general, your damping increase with the phase margin. Pay attention, this is the phase margin computed on L, and this is the damping of F, of the closed loop of Y over Yref. And the same for the peak. The peak decreases, increasing the phase margin. So in general, we can say that if you have some specification of damping and of maximum peak, maximum overshoot, you might try and achieve them by setting a certain phase margin. For example, 60 degrees is not bad. Then you might try and see what you get, and if this damping, this D coefficient is not satisfactory, you might try and redo your tuning by decreasing a little bit the phase margin until you get something that is satisfactory. So, just to summarize how we do synthesis under frequency domain specification. We translate the specification into frequency domain. Then we choose either a fixed control structure from a catalog, which we are going to see shortly, or we use the loop shaping approach, which we will not show here. Then we have to tune the controller, and in the case of the predetermined structure, basically each specification will translate into an equation involving the design parameters. So this means basically that if you have a certain number of specifications, you will need to have at least as many parameters as the number of specification, so that the equations or inequality that you will write are enough and are not more than the number of parameters. Otherwise, you don't have a solution. It is the same as an algebraic equation. If you have a certain number of unknowns, you need at most the same number of equations in order to have a solution. And how do we work the thing? We work everything on the Bode plot of L, so the modulus, the gain, and the phase Bode plot, which is the sum of the Bode plots of C and H in both gain and phase. The gain in decibel sums up, if you have a product of two transfer functions, C and H, namely in this case, the logarithm of the modulus sums up. So basically you can get the gain Bode diagram of L from the sum, the algebraic sum of the diagrams in decibel of C and H, and the same for the phase. The phase sum up, so the phase of L is just the phase of C plus H. So basically H is what we start from, then we will add C to the diagram of H in order to get the diagram of L, and we need to pay attention in order to tune the parameters such that L is the one we want. Okay, so let's continue with this. Let's see which are the predetermined control structures that we might want to use. So the first one, the simplest that you can think of, is what we call the proportional control, which means basically putting a proportional gain here, just a scalar over here. And this comes from a very simple intuition, a very simple observation. Just look at this diagram over here. What do we want? We want H to converge to, we want Y, sorry, to converge to YRF. So if Y is bigger than YRF, then basically we will need an action that brings it down. And the farther it is, the stronger this action. And if Y is on the other side, then we will need an action that brings it up. And it makes sense to have this action stronger if the distance is bigger. So basically, it makes sense to have U proportional to Y minus YRF with an opposite sign. That's why we have this minus sign over here. So this brings us to the proportional control. Basically, as you see, U is a proportional gain, we call it, a Kp, a scalar, times YRF minus Y. And this, of course, translates in Kp times epsilon, which means that C is just Kp. Very simple, very simple. Then we have another kind of control structure, predetermined control structure, which is the derivative control, which is usually coupled to a proportional one. So let's just assume that the proportional controller alone gives you a certain response like this. And this is okay, but you see that at a certain point you have too many oscillations. So what we would like to do maybe is to reduce the oscillation. And the oscillation is not so much dependent on how far you are from the reference, but also on the speed at which you are moving away from the reference. So typically, in order to reduce the oscillation, you might want to set a term, a control term, which goes against the change of the value of Y, so the rate of change of Y, so basically the derivative of Y. And that's why you can read it here. I think is explained very well. If Y oscillates too much, changes too quickly, goes up and down, so it has big derivatives, big time derivatives, you should penalize the rate of change of Y. You should put a control term which goes against its derivative. And that's why you can add as an additional term to your controller, starting from a P controller, proportional controller, you can add a derivative control. Again, multiply the derivative of the error, derivative of the input over here, the input to the controller. And this will try and reduce the effect of the derivative terms. Let's say we'll try and reduce the formation, if you want, of high derivative terms, because it will act before they grow to I. In terms of transfer function, the transfer function of C will be Kp, if you just Fourier transform, Laplace transform, sorry, this one, you will have Kp plus Laplace transform of the derivative is S, Kp plus Kds, which you can also factorize in these terms. You factorize Kp and then you get a tau multiplying S, and basically Kd equal Kp tau d. So just to understand a little bit more how it works, look at this step response. If you have a proportional controller, the action in A and B will be the same, because the distance between the reference and Y is the same in A and B. What is the difference in the two cases? In A, the signal Y is going far away. Instead, in B, it is already going through to the good direction, towards the good direction. So actually, you need a stronger action here in A than in B. In B, basically, you don't need to do a lot because your derivative is already bringing you towards the good direction. So in fact, if you have a derivative term, this is what it happens. Here, the proportional term is the same in the two cases, but the derivative term will get you an additional push towards the reference. Instead, here, you have a negative effect of the derivative, so that it will basically have a smaller input, bringing it towards the reference, because it is already going towards the reference, and so you don't need to push it too far. What is the problem? If you push it too hard here toward the reference, you risk overshooting again, and that's why you will oscillate and oscillate again. So that's why we can say that derivative control has an inherent stabilizing effect. Let's look at another thing you might have. You might have a situation like this. Let's look at the picture where you have your step response and your value of Y stabilizes very well, not so many oscillations, so everything very nice, but it stabilizes to a value which is not the reference. And that basically means we have a non-zero steady state error to a step response. And as you already might remember, the solution to this is adding an integrator in the loop. So that's why we can add an integrator to a proportional controller and get what we call a proportional integral controller, the PI. But let's try to understand also more intuitively why an integral controller basically solves this problem. You might have, in fact, something acting over here that even with the proportional controller on, you push down, so you have an action, proportional action, trying to push this thing down to YRF, but it is not enough because of some other effect. If you have an integral control, basically your control action also depends on the integral of the error over time, basically the integral of this distance over here. So U will grow with time if this one doesn't go to zero. Okay, so you cannot have an equilibrium like this if there is an integral action, because U will always grow. So the only equilibrium possible is with Y equal to YRF. That's why the integral control brings this Y to the reference. You can imagine that it grows until it is strong enough to counteract the effect, whatever it is, that keeps Y far from YRF. So if we write it down, the integral proportional controller has this structure over here. Proportional with respect to epsilon plus a constant, again a scalar constant, times the integral of epsilon over time. And in terms of transfer function, in terms of Laplace transform, you get Kp plus Ki over S. The integral becomes 1 over S, which you can also factorize in this way. You just write it as Kp times 1 plus 1 over tau is, where tau I has the dimension of a time. And if you put them all together, proportional, integral, and derivative, you want to have something that brings your reference and your output together, proportional. You want to limit the oscillation, derivative. You want to have zero steady state error, integral. Then you get the three terms together like this, which you can also factorize in this way in terms of Laplace transform, in terms of transfer function. And again, tau I and tau d have the dimensions of time. They are seconds. We have just a little problem with this formulation that consists in the fact that the derivative is non-causal. It's something we have already discussed previously, I think. What it means that it's non-causal, you cannot compute a derivative in real time. At that given instant, you don't know what your signal is going to do in the next instant. And that's what you need in order to compute the derivative. So basically, in real time, you cannot compute the derivative of a signal. So that's why the derivative is usually replaced by a pseudo-derivative, which is basically the derivative just computed a little bit of time earlier than the present instant. And so this consists basically in adding a low-pass filter, a pole, a denominator, to the derivative term. This extra term here, 1 plus s to f at the denominator of kds, which basically brings the numerator and denominator to degree 1, which means causal. And you can change it both in a PD or in a PID, and you get these formulations over here. How should I choose my tau f? Well, basically you should choose a time which is small enough such that basically this transfer function is very similar to a derivator up to the frequency where you need it to work, which is mainly the crossover frequency. But we will see some examples of this later on. So let's just see what they look like in terms of Bode diagram. So proportional controller, just a standard static gain, let's say, a scalar gain, has a flat magnitude at all frequency, doesn't depend on the frequency, and the flat phase doesn't depend on the phase. This is the case for Kp positive. If you have a negative, well, we change, but we will not use in general negative feedback. If we have a Pi, well, we just write it down, factorizing it in this form over here. Then we can just basically solve in order to obtain the numerator, and then basically we end up with this one, which shows that a Pi controller is a pole in 0, which gives you the Bode diagram starting with a slope of minus 20 dB per decade and a minus 90 degree, and then at a certain point we have 0. Tau is positive, tau I is positive, so we basically have a real negative part, a negative real part 0, which at a certain point, basically at frequency 1 over tau I, will increase the slope, bringing it from minus 20 dB per decade to 0, and increase the phase, bringing it from minus 90 to 0. So basically this is the Bode diagram of a Pi controller. Of course, these minus 90 degrees are not nice because they bring you close to the minus 180 that you want to avoid when you are taking care of the stability and the robustness. So what you have to make sure is that this thing is completely gone away, so you have to be in this area when you hit the crossover frequency of L. We'll see some examples again. For a PD, if we write it down in the causal form, so with the denominator, with the pseudo derivator over here, we can write it like this, and then we solve for the numerator again, and we get this stuff over here. Then we said that usually tau f is small, so we make the assumption that tau f is a lot smaller than tau d, so we can basically approximate with this formula over here. So there is an s missing over here, of course, 1 plus s tau f, 1 plus s tau f. So basically this is if you pay attention, it is just how to say, it is just pole and the 0, right? A pole and the 0, and this pole and zeros are located at a position which depends on what? On tau f and tau d, right? So which means that your mode diagram starts flat, because n0 is 0, no integrator, no derivator, even if it looks like there is a derivator, but when you solve the fraction it is not. So you have a flat 0, then usually you have this one coming first. So you have a 0 coming first, which brings the slope up to 20 decibel per decade, phase up 90 degrees, and then at a certain point you will have this one coming later on, which brings the slope down again and the phase down again. So basically this one is the dashed line. If you had the ideal PD, this one PD, then you would not have this denominator over here, and then your slope will not go down here and your phase would not go down here. But this of course is not realistic. You always have the dashed line because you always need to have the denominator in order to make it causal somewhere. And then last but not least, if you have the full PID, well, you get basically this, and you can basically work it out, and it contains basically 2 poles and 1 0, and the 2 poles, one of which is in 0, so you start sloping down at -90, then at a certain point you will reach 2 zeros, you will reach 2 zeros, so it will go up twice, let's say to -20 to +20. If you just solve this one, you will see you have 2 zeros. There is actually a tutorial that works this computational out. It is the last one, very interesting to see. And then if you have this filter over here, you will have the slope going down again because of the last pole, and the phase going down again to 0, because it's a second order up and second order down. There you go. So just to have a table which summarizes the effect of each of the components. Of course, you can basically take any contribution and create your controller. Usually the proportional contribution is always there. Then you can choose to add integral and or derivative contribution. But we should not rule out the possibility of purely derivative or purely integral controller, so depending on the case. But in general, you will always put the P part. So what we have is either a P, a PI, a PD, or a PID control. And let's just to see what they do, each one of them. So what's the good part and the bad part of each of them. So the P basically stabilizes the system, is the simplest idea you might have to do it, because it tries to reduce the error, basically works directly against the error, the instantaneous values of the error. What's the problem it can have? The drawback of a P, if the gain is too high, it can destabilize your system. And this we have seen it in the example of the first controller, which we are trying to tune at the end of class 4, which we've done both in using the root criterion and both in another way, and it is also featured in my MATLAB example. So P is good. You might want to push P, the KD, the gain, the proportional gain, this scalar, you might want to push it very big, very high in order to achieve your performance, but pay attention. If the gain is too high, you must destabilize the system. Integral controller. So why do we want to add an integral controller? The reason for it is to cancel steady state error, and also to cancel the effect of constant disturbances, as we have seen in the class number 4, if I'm not wrong. Problem is, as we've seen just now, it gives you -90 degrees of phase. -90 degrees of phase. And that's -90 degrees of phase brings you close to the -180 degrees, which are at the critical point, and so again it is a destabilizing effect which we might try to avoid. The derivative control reduces the oscillation because it works against rates of changes of the signal. Okay, it doesn't like the signal to change, and this is also interpretable in the fact that it gives you +90 degrees of phase, so inherently stabilizing effect. What's the drawback? Slows down the system, and it might amplify a measurement noise. Why? Because if you have a high frequency noise entering the system, the derivative will basically amplify it. If you have a system that changes a lot, the derivative will change even more. So you have to pay attention if you have noise in the system that the derivative control does not amplify it. And this is one of the reasons more to add the filter, not only for causality but also for filtering away this high frequency noise. Let's see a last two examples of predetermined controller. One is the phase lead controller, for which we'll see some example, which is basically very similar to one of the controllers we already seen, but we will parameterize it with this structure. Basically, it is a constant gain times a zero and a pole, and basically this constant a, it should be greater than 1 such that the zero comes before the pole. And that's why you might ask this is useful, because if you have the zero coming before the pole, you will have the increase of phase before the decrease of phase. So basically at a certain point in the Bode diagram, at a certain omega m we call it, you will have a delta of phi going up, a phase going up, an extra phase. And this thing is something you might need just to get the phase margin that you want in a certain loop transfer function. Imagine you have a loop transfer function, you want to have a certain omega of a crossover frequency, but you set your crossover frequency at that phase, your phase is too low, so you cannot get the phase margin that you want. You might add this controller over here to get the extra phase at the exact point where you need it in order to increase your phase margin. And how do you get this thing? Basically, there is a recipe for tuning it, and you have basically to choose at which omega m you want this extra phase. Typically, you want it at the crossover frequency. Typically, not always. Then, once you have decided which is your omega m, you have to decide what is your delta phi, your extra phase that you want. And then your recipe will give you the numbers over here. Okay, choose delta phi and omega m from specification. A is given by this expression, and tau L is given by this other expression. Last but not least, you will have to tune KL, and typically you will have to tune KL in order to make sure that the overall gain of L is 0 at the crossover frequency, typically, so that actually the crossover frequency is the crossover frequency that you wish. An approximate tuning is in general possible in many cases. Last, not so important, but we will talk about, is the phase lag controller, which just does the opposite. So it's the same formula with the a smaller than 1, a greater than 1 at the denominator, sorry. It's the same formula with a moved to the denominator. And then in this case we have basically the pole coming before the 0, so the net effect of phase is negative, which in general you might think is not such a smart idea to have. You might think that negative phase is destabilizing, but in certain cases you might want to destabilize the system because it is too stable. For example, if you have too much phase margin, you might want to reduce it because your system will be too slow otherwise. So that's a case where you might want to use phase lag controller. Now that's the end of the story for today. We have seen these predetermined controller forms. Now, of course, it is not so obvious to use how to use them, and that's the topic of the next class, and which we will see through examples. And these examples are interesting because you will see that all the steps of the tuning of the controller, from the specification to the choice of the kind of controller, ending up with the tuning. And for the tuning, just a warning, you need to be able to draw a Bode diagram and to understand also a minimum of computation in terms of complex functions, because you might need, for example, to compute the value of a phase of a function or of the modulus of a function. For this you need to remember a little bit what we've seen in the first classes. How do you compute a phase or a modulus of a transfer function for a given omega. Which is also possible to do sometime by using a computer and drawing the Bode diagram directly. But it is important to be able to do it also by hand. So I suggest you try and review this part a little bit before looking at the next class. Otherwise, that's all for it now. And thank you for listening, and stay safe, everybody.